Good morning. My name is Jack Madden. I'm a senior project engineer with Erdman Anthony. Today's presentation is on positive train control, focusing on the northern New England states. The railroad industry has been in existence for nearly 200 years. Positive train control is the most significant change in train control systems in the last century. As engineers, knowing how PTC works and its future interaction with the highway network will help you in your future projects. Today's presentation is divided into 6 sections. I will provide an overview of how the railroad signal control systems work and an introduction to some railroad definitions. We will discuss the 2008 head-on collision in Chatsworth, California, which was the precipitating event that led to the congressional mandate for PTC. We will discuss what PTC is supposed to do and how it works. We will discuss the 2 types of PTC on railroads in northern New England, and we'll touch briefly upon Connecticut and Rhode Island as well. And finally, we will discuss future developments in PTC in northern New England and nationally, which some are referring to as PTC 2.0. So initially, our introduction and the railroads of New England and the basics of railroad signal control systems. This map was taken from the CSX transportation filing with the Surface Transportation Board to acquire Pan Am Railways. Our area of interest in today's presentation are the states of Vermont, New Hampshire, Maine, and Massachusetts, the entry into Vermont and Massachusetts from northeastern New York State. We will briefly touch upon entry into Massachusetts from Connecticut and Rhode Island as well. Trackage rights is a term describing the contractual agreement under which trains of one railroad have the right to operate over the railroad lines owned by another railroad. This slide contains the miles operated in northern New England. The Surface Transportation Board divides freight railroads into 3 classes based upon revenue. As of 2019, STB Class 1 railroads are those which have over $504.8 million in revenue. Class 2 are railroads with over $40.2 million, and less than $40.4 million are Class 3 railroads. Regional and short line railroads are terms used by the Association of American Railroads, an industry association, that are roughly equivalent to STB Class 1 and Class 2, respectively. There are 2 class railroads in northern New England: CSX Transportation, which enters Massachusetts from New York State, and Canadian Pacific Railway, which enters Maine from Quebec. There are 4 regional railroads: New England Central, which enters Vermont from Quebec and runs south through Vermont, New Hampshire, and Massachusetts into Connecticut; Pan Am Railways, which enters Vermont from New York State and runs east through Vermont, Massachusetts, and Maine into New Brunswick. Pan Am has branches north into Vermont and New Hampshire and south into Connecticut. Pan Am Southern is a joint venture owned by Norfolk Southern Railway and Pan Am Railways. Pan Am Southern owns and operates that portion of the Pan Am Railway network from connection to CSX Transportation in Rotterdam Junction, New York, east to the Norfolk Southern Mechanicville, New York Intermodal Automotive Terminal, and east on to the Norfolk Southern Air Mass Intermodal Automotive Terminal. It also operates north from East Deerfield, Mass. To White River Junction, and south from East Deerfield, Mass. Through Springfield into Connecticut. Providence and Worcester Railroad operates from Worcester, Mass. South into Rhode Island, Connecticut, and Rhode Island and Connecticut, and west onto Fresh Pond Yard on Long Island. New York Central Railroad and P&W are subsidiaries of the Genesee and Wyoming Industries. There are 22 short line railroads. I will only highlight 2 of them: the Clarendon and Pittsford Railroad, which enters Vermont from Whitehall, New York to Rutland, and the Vermont Railroad, which enters Vermont from Hoosick Junction, New York, runs through Rutland, Vermont to Burlington, Vermont. CLP and VTR are subsidiaries of Vermont Rail System. Amtrak operates from Albany, New York into Massachusetts east to Boston, from Whitehall, New York into Vermont east to Rutland, from New Haven, Connecticut into Massachusetts, Vermont, and New Hampshire to St. Albans, Vermont, from Providence, Rhode Island into Massachusetts north to Boston, and from Boston north into New Hampshire and Maine to Brunswick, Maine. MBTA operates 398 route miles in the Boston metropolitan area. Now, this map is an extract of the Amtrak service route map contained in the CSXT application to the STB. Real quickly, you can see in the chartreuse line is CSX transportation east from New York State to Boston. Canadian Pacific Railway is off the map in northern Maine. Pan Am Southern is in red, and then again, that comes east from New York State to Air, Mass, goes north to east from East Deerfield to White River Junction, and south into Connecticut. In blue, Pan Am Railways continues from Air, Massachusetts through New Hampshire, Maine into New Brunswick, with branches into New Hampshire and Massachusetts. CLP operates from Whitehall, New York into Rutland, Vermont. And then Amtrak, of course, operates Albany to Boston, Albany to Rutland, New Haven through Springfield and on to White River Junction to St. Albans, Vermont. Northeast Corridor service from Boston, or to Boston from Rhode Island, and down easter from Boston North Station into Brunswick, Maine. There are two categories of track. These are official definitions, but just remember that controlled track is where a train dispatcher controls the movement of trains, either through a railroad signal control system, which we'll talk about shortly, or by verbal authority between block limit stations. Non-controlled track is a track in which trains can move without authority of a train dispatcher. PTC systems are placed over controlled track. Now, in northern New England, there are four types of signal systems. You have wayside signal systems, where about every 2 miles and at interlockings, there's a signal mast which can display a combination of green, yellow, and red lights to convey signal indications to the locomotive engineer. The maximum authorized speed with wayside signals is 79 miles an hour. Cab signal systems and wayside are the same as wayside, but also displays the signal indications on a console in the locomotive cab. The engineer can change his speed based upon the instantaneous change in the signal indication, rather than waiting up to 2 miles for the next wayside signal. The maximum authorized speed is over 79 miles. That's what it's allowed. Cab signal systems only is the same as cab signal and wayside, but there are no wayside signals, except for home signals governing entrance into an interlocking. Maximum authorized speed of over 79 miles an hour is allowed. Dark territory are rail lines where there is no wayside or cab signal systems. Movement is governed by verbal authority of the train dispatcher between specific block limit stations. Maximum authorized speed is limited to 59 mile an hour for passenger trains and 49 mile an hour for freight trains. Here's some additional definitions. Again, these are official definitions, but just remember, an interlocking is a station location in controlled track where a train can change from one track to another on a multiple track main line or divert from the main track to a branch line. A home signal is a signal controlled by the train dispatcher which governs movements into an interlocking or a controlled point. A controlled point is a station location in controlled track where the train dispatcher controls the signal. Now, here are some more definitions specifically toward the signal aspects. This is a simplification of signal aspects, which the engineer would see either from wayside signals or on the controlled signal display in the cab of the locomotive. A green light aspect conveys normal speed, which means that the train can proceed at the maximum authorized speed for that particular block of the track governed by the signal. A yellow light aspect conveys approach, meaning that if the train is moving greater than medium speed, which is 30 miles an hour, the engineer must slow the train to 30 miles an hour before passing the signal and must be prepared to stop at the next signal. A red light displayed over a yellow light, this aspect conveys restricting, which means the engineer must slow the train to a speed so as to be able to stop the train in 1/2 of the range of vision in any event not exceeding 20 miles an hour. A red light aspect means stop. Depending upon location, this may allow the train to proceed at restricting after stopping. All right, now we're just going to quickly go over the basic operation of a signal system. Wayside signals are placed about 2 miles apart. For train movement, the clear aspect, the green light, allows the train to pass the signal at the maximum authorized speed. As the train approaches the approach aspect signal, it tells the engineer to slow the train to 30 miles an hour before forcing the signal and be prepared to stop at the next signal, which you can see is red. The stop aspect tells the engineer to slow the train and stop at the next signal. The accident, which precipitated positive train control, occurred at about 4:22 p.m. Pacific Daylight Time on Friday, September 12th in Chatsworth, California. This is an overview of the accident area. The slide and those immediately following this were taken from the National Transportation Safety Board's report of the accident and a briefing by the California Public Utilities Commission. This slide is a Google Maps photograph of the accident site. At the top left is the tunnel from which the Union Pacific Railroad local train exited. At the lower right is the home signal at the interlocking where the Metrolink commuter train ran through or past the red signal where the engineer was supposed to stop. The point of impact is the location where the trains collided head-on. The photo in this slide and those immediately following were taken by the National Transportation Safety Board during the reconstruction of the accident. This is the view which the Metrolink engineer saw from the cab of his locomotive as he approached control point Topanga. He was supposed to pull forward and stop at the red home signal. The train dispatcher had lined the switch for the oncoming Union Pacific Railroad local train so that it would pull into the siding, and after it cleared, the train dispatch would then line the switch for the Metrolink train, and the signal would then display a green aspect indicating clear for the Metrolink engineer. The Metrolink engineer, however, did not stop at the red signal. You now have the view which the Union Pacific locomotive engineer had as the Metrolink train rounded the curve. 1001, 1002, 1003, 1004. The Metrolink train and the Union Pacific train closed at a speed of over 80 miles an hour. The Metrolink train derailed its locomotive and lead passenger car. The Union Pacific train derailed its 2 locomotives and 2 of its 17 cars. The force of the collision caused the locomotive of the Metrolink train to telescope into the lead passenger coach by about 52 feet. The accident resulted in 25 fatalities, including the engineer of the Metrolink train. The engineer and conductor of the Union Pacific local train survived. They were trapped in the cab of their burning locomotive, which was on its side, and were rescued by firefighters as the cab filled with smoke. Emergency response agencies reported transporting 102 injured passengers to the local hospitals. Damages were estimated to be in excess of $12 million. Now, I'm not going to read this quote from the NTSB report, but I will note that the NTSB found that the absence of a PTC system to stop the Metrolink train at the red signal was a contributing cause of the accident. Congressional Action was swift. Slightly more than a month after the accident, President George Bush signed the Rail Safety Improvement Act of 2008. This mandated PTC for certain levels of train operation on controlled track and an increased safety requirements in dark territory. We're now going to discuss exactly what is PTC. Now, the PTC functions under RISA 2008 are these four: prevent train-to-train collisions such as at Chatsworth, prevent overspeed derailments, that is, force the train to keep at or below the speed limit for the track that is operating on, prevent incursion into roadway work zones, that is, force the train to slow and stop at temporary work zones where railway workers are working on the tracks, and finally, prevent movement of a train through a switch left in the wrong position. This is primarily in dark territory where there is no signal system into which the switch could be electrically connected, indicating that it is in wrong position. Now, on freight railroads, these are the requirements that PTC imposes. On Class 1 railroads whose lines have 5 million gross tons per day, which is about 100 loaded freight cars, and any amount of poison inhalation hazard or toxic inhalation hazard traffic. All it takes is one car of poison inhalation hazard or toxic inhalation hazard per year to trigger the requirement for PTC. On Class 2 and Class 3 railroads, an exception is granted regardless of the tonnage or number of TIH or PIH cars handled if there are no passenger trains. Now, on passenger railroad territory, all intercity passenger and commuter railroads must have PTC. The FRA can grant exceptions where there are limited freight operations in either signaled or dark territory and Class 1, 2, or 3 railroads. Class 2 or 3 lines with 15 million gross tons or less and having fewer than 6 pairs in signal territory or 2 pairs in dark territory of passenger trains have an exception. This is the exception that allows Amtrak Downeaster service to operate up to Downeaster service up to Brunswick, Maine without PTC, and the Amtrak Ethan Allen to operate one round trip from Whitehall, New York to Rutland, Vermont. On freight locomotives, now in addition to the physical territory in the ground, locomotives have to be equipped with PTC. PTC has to be installed on all Class 1 railroads locomotives. Class 2 and 3 railroad locomotives have an exception, which operate trains over Class 1 lines up to a limit of 4 trains per day and up to 20 miles. On passenger locomotives, PTC has to be installed on all Amtrak locomotives and cab cars. PTC has to be installed on all commuter railroads, locomotives, EMUs, DMUs, and cab cars. Tourist and excursion trains have an exception under the 20-mile limit. By the December 31st, 2020 statutory deadline set forth by Congress, FRA announced that PTC technology is in operation on all 57,536 required freight and passenger railroad route miles. This is down from the approximately 70,000 estimated in 2008. The number of locomotives and the number of wayside interface units are listed here. It is not known how many have actually been installed yet. And also, no one is quite sure what the total cost for PTC will be, only that the estimate has continually increased since PTC was mandated in 2008. Some more definition. This slide quotes the definition of PTC right from Section 21-154 of the RISA legislation. It includes the big 4 functions which we previously discussed. A major issue for the industry has been nailing down the interoperability of locomotives of each railroad to operate over the rail lines of another railroad using the PTC of the host system. Okay, so how does PTC work? Each railroad's PTC system has a back office system in their IT department or the train dispatcher's office, into which all the data associated with that rail lines is loaded as indicated here. Onboard system is on each locomotive that the railroad has, which communicates to the back office system by railroad. Each locomotive has a bubble running ahead of it with a warning speed curve and a braking speed curve. The back office system continually communicates with the onboard system to tell the status of the signal ahead. When the yellow curve hits the signal, the system warns the engineer to slow down. If the engineer has not done so by the time the red curve hits the signal ahead, then the system applies the brakes. Earlier, we mentioned that the railroad's train dispatching system has to interface with the back office system. In addition to this, the back office system has to interface with all the wayside interface units throughout the railroad's network. Wayside interface units are installed at every signal, control point, switch, grade crossing, station location, and so forth. It was estimated that there were about 70,000, but the total number is still being calculated. Next, we're going to discuss the two types of PTC installed on railroads in New England. There are two types, ACEC and ACEC-NH. ACEC is the automated civil speed enforcement system, pronounced ACEC. It was developed by Alstom for Amtrak, and as of the RISA legislation in 2008, it was in use on Amtrak's Northeast Corridor. IETMS is the interoperable electronic train management system. It was developed by Wabtec for BNSF. As of the RISA legislation in 2008, it was in use on one Burlington Northern Santa Fe Railroad subdivision in Illinois. In 2008, the BNSF, Union Pacific Railroad, CSX Transportation, and Norfolk Southern signed an interoperability agreement to use IETMS for their railroads. Other freight railroads joined, and this became the standard PTC for the freight railroads. Now, this is an overview of IETMS. It is a communications-based PTC system overlaid on existing train control systems, either wayside, cab signals, or dock territory. Location determination and navigation are provided using GPS. The back office system communicates with the locomotive onboard systems and the wayside interface units via 22 megahertz data radio. The loco onboard system is constantly processing data from the back office system, the wayside interface unit, the onboard database, the GPS receiver, and the locomotive axle tachometer in order to enforce train movement. What's in the onboard database? I'm not going to read all of these, but they illustrate the complexity of the data included in each locomotive's onboard system. Now, this is an overview of ACEC. Unlike IETMS, ACEC is a transponder-based PT system overlaid on existing cab signaling systems. You have to have cab signal systems in place for ACEC to work. The back office system communicates with the loco onboard systems in the wayside interface units via the 220 megahertz data radio. The original ACEC system Amtrak had was 900 megahertz, and they had to eat the cost to convert this over to 220 megahertz. Now, to enforce train movement, the ACEC onboard system obtains the fixed data from the transponder, such as current location, grade, distance to the next signal, and so forth. It's prompted to communicate with the back office systems, the wayside interface unit, to obtain and process data. Now, transponders are mounted between the rails in groups of 2 to 4. Each transponder contains unique identification data, such as the railroad code set by FRA and line number, track identification, and location of the track. Each transponder also contains location-specific data, such as the civil speed limit locations in both directions from the transponder, and the distance to the next transponder and for both directions. This is a photograph of what an ACEC transponder looks like. They are installed in pairs so the system can identify which direction the train is moving. Next, we're going to do a quick comparison of ACES and IETMS. For train location navigation, ITMS uses GPS signal, whereas ACES detects the programmed transponders mounted on the track. For navigation, IETMS uses a combination of the axle tachometer and GPS signal. For train navigation under ACES, they use the combination of axle tachometer and the detection by the fixed transponders. The track determination is made initially by a locomotive engineer entering into the locomotive where he starts, where the locomotive is, and then the switch position as the train moves is followed along. For ACES, the track determination is made by a combination of fixed transponders and switch position. For enforcement of speed limits, the permanent speed limits are on the locomotive onboard system in IETMS, and for ACES 2, the transponded data contains the maximum track speed and all permanent restrictions. For enforcement under IETMS, it's based upon the current locations, train type, travel, and signal aspect received from the wayside interface unit. And for ACES, it's based upon the current location, train type, travel direction, and the cab signal aspect. Okay. Next, we're going to talk about the PTC systems installed in northern New England. This is a map of the MBTA system. They have ACES installed. Amtrak locomotives, which operate over the system, the MBTA system, have ACES installed, and Pan American Railways has ACES installed on their locomotives to provide freight service on the north side lines, north of Boston, on MBTA, and CSX has ACES installed in their locomotives on the south side to provide local freight service there. Now, getting out a little bit in the map, CSX has an IETMS installed on their rail line from the New York, Massachusetts line to Worcester. Amtrak has ACES installed on their railroad line from the Connecticut, Mass line up into Springfield. Now, the railroads which have locomotives PTC installed on their locomotives, Amtrak has to have IETMS to operate on the CSX transportation main line from New York, Mass border to Worcester, where they then go on to MBTA. And Pan Am has to have IETMS on the Canadian Pacific Railway from Mechanicville, New York to Schenectady, New York, at the far west end of their system. Now, I mentioned that we had to go a little bit into southern New England, and I'll just briefly point out here that Amtrak has got ACES installed on their system from Springfield to New Haven. Amtrak has ACES installed from the Massachusetts, Rhode Island line to New Haven, Connecticut. And the Metro-North Commuter Railroad has ACES installed on their line from New Haven into New York City. And you can see below the railroads which have PTC installed on their locomotives so they can operate on the different host railroads. In conclusion here, we're going to talk about future developments and PTC 2.0. As I had mentioned, CSX has filed application with the Surface Transportation Board to acquire Pan Am Railways. CSX is committed to work with Amtrak to install ITMS from the Mass New Hampshire state line to Brunswick, Maine. Now, this will allow the Downeaster service to extend beyond the current 6 round trip per day limit. New Hampshire DOT is in the project development phase for the Capital Corridor Rail Project, which is an extension of the MBTA from Lowell, Mass to Manchester, New Hampshire. This would require installation of cab signal system and ACES. Amtrak is working with the Clarendon-Pittsford Railroad and the Vermont Railway and the New England Central Railroad on META, Main Line Track Exclusion Addendum, to improve safety. Now, both of these lines were suspended during COVID-19, so I'm not quite sure when this experiment is going to happen. Now, for PTC 2.0, the Illinois Commerce Commission is testing with Amtrak on Canadian National Chicago to St. Louis line, trying to fully integrate PTC with crossing activation. They will use the Wayside Interface Unit and the track database and radio communication to control the active warning devices. They will not use track circuits. The future goal will be to include a vehicle intrusion detection system at grade crossings to interface with PTC and reduce the train speed to restricting if a highway vehicle is present. Now, out in Colorado, the Denver Regional Transportation District Eagle project is attempting to use or is using PTC to control crossing activations. This is the first system installed in the United States with PTC included in the original construction, not as an overlay. The system was done under a design, build, operate, finance, maintain program for a 40+ year project life. And they use a wireless crossing activation system integrated with PTC. And they use track circuits as a backup if there is a failure. Now, continuing on, the Association of American Railways has got a Train Control and Communications and Operations Committee. Participants include the AAR, APTA, the American Public Transit Association, the American Shortline and Regional Railroad Association, and terminal railroads. They've got a long list of top-ranked projects that they are working on. And an extract of 3 of them are: develop a high reliability and capacity control to analyze the operational effects of high reliability and capacity control. They want to come up with something called a quasi-moving block. You remember our discussion of the bubble around a train. If they have this bubble can move along with the train, they might be able to reduce the space between trains and thus increase capacity of a rail line. The second item is the PTC interoperability support. As I mentioned, this has been a particular problem for the freight railroads. And then finally, train control and cyber security. They are looking at issues involving GPS spoofing and jamming of the PTC 220 megahertz radio system. So ladies and gentlemen, that concludes my presentation. If you have any questions, I'll be happy to answer them. Thank you very much for your time.